Good afternoon, everyone. So in this talk, I'm going to show you a new method to deghost the data right on the cable. Say with this method, you can deghost your actual acquired data. And as Dr. Wang explained, the reason for we to look at this is because the current deghosting method with the Green theorem cannot deghost the originally acquired data, but always deghost a new data set. And the current method has been discussed in few presentations earlier today, and it is the Green theorem-based deghosting method in X-omega domain. And next, I'd like to use a very simple schematic to remind you the general idea. So this is a marine experiment, and Fs is the free surface, OB is the ocean bottom, and the red star is the source in the water column. The blue line here is the receiver cable. So the unique advantage of this current method is that it can effectively accommodate a horizontal cable and a non-horizontal cable, as my colleague Zheng and Jing Wu have shown you their result by accommodating an undulating cable. However, for both horizontal and non-horizontal cable, the current method can only deghost the data at a depth that is above the cable, not on the cable, as these green dashed lines are shown here. In fact, the method deghosts a new data at a new depth, but not the actual acquired data. Well, how does that happen? Dr. Wang has given an explanation, and I'd like to quickly remind you that reason here. And this is the Green theorem-based deghosting algorithm in X-omega domain. And you can see the P up here is the outgoing wave of the deghosted data at the point R, as highlighted by the red star in the picture below. R here is above the acquisition cable and below the source point RS, which is highlighted by this red star here. And move to the right side, we have the acquired data P and its normal derivative. You can see that R prime is here actually the integral variable along the cable, and it's highlighted by the yellow dot on the cable. So then you need to have a Green's function and its normal derivative in the reference medium. For both of them, they are actually starting from the output point R and ending at the receiver point R prime. So now, if we give a specific output point R and a specific frequency, then you can see both G0 and the grad G0 are actually the functions of R prime. So they can be plotted in terms of R prime, and for example, it will have a shape like this. This is G0, and the grad G0 has a similar property here. Now you can see the peak happens at a place where R prime and R has the closest distance. And when R is far from the cable, you can see the shape now is wild and mild. Now we move down, we make output point R moves down and gets closer to the cable. You will see the change of that shape. It gets sharper and narrower. When it keeps moving down, it becomes extremely narrow and sharp. So you can imagine that when R is approaching the receiver cable, the major contribution of this integration comes from this extremely narrow zone. So when we do when the seismic acquisition is actually performed with the finite sampling interval, as shown with these discrete points here. And so when we carry out this algorithm, a finite sum is actually used to numerically approximate this integral. So the value of G0 and grad G0, especially the peak value here, may not be picked up, and the quality of deghosting may fall off. So this is the reason that precludes the output point R being too close to the surface, and it cannot be on the surface itself. So here in this talk, we are pursuing a method to deghost the data right on the cable. Now, if the cable is horizontal, Then we can transform the algorithm from X omega domain to KS omega domain. And then, as Dr. Wagner explained, you can locate the output point on the surface. As you can see, the green dashed line, which is the output, and is sitting on the blue line, which is the actual cable. So, however, if the cable is non-horizontal as shown like this, the transform from X omega to KS omega cannot be easily achieved. And you have to go back to the S omega domain formula, and which in principle can accommodate a non-horizontal cable. And you have to locate your output point above the acquisition surface. So in this talk, we are showing you a new method to deghost the data right on the cable, still in the S omega domain, to get the actual acquired data deghosted. As you can see, the green dashed line is the output surface, and the blue line is the acquisition cable. They overlap. And the cable itself is without limitation of the shape. It can be with a random shape, in fact. So it takes 2 steps to finish the job. The first step is we use the acquired data on the cable, the pressure P and its normal derivative as input to predict a data at a depth above, and that is deghosted. As you can see here, the output is the input is on the blue cable, and the output is on this green dashed line. This is actually what the current method performs. So the second step is actually new here. We use the output result from the first step as input to predict the deghosted data on the cable. You may have already realized that this is a one-way wave prediction to predict the data from top to the two depths. So next, let's look at the detail here. This is a marine experiment, and you have this black curved line is the acquisition cable, and their data acquired on this cable. So our objective here is to deghost the data right on the cable. And move to the first step, we need to predict the deghosted data that is above the cable by using the Green theorem-based deghosting method. So this method, you need to pick up a reference medium and then characterize the difference between the actual and the reference as the source. So what we do is we choose the reference medium to be composed by a homogeneous water whole space. Then you will have 3 cells acting on this, as we explained in the previous presentation. The first source is the energy source, and the second source turns the water to be air above the free surface, whereas the third source turns the water to be earth below the ocean bottom. Now, if you have a point R below S1 and S2 and above S3, then the contribution from them are like this. Both S1 and S2 contribute to the down wave, and the S3 contributes to the only up wave. So the interest here is we like to obtain the outgoing wave contributed by the source S3. So what you need to do is put a closed surface around, highlighted by this blue box, and evaluate the Green theorem at a point inside the volume. Then you can obtain the contribution from the source that is outside the volume, that is going up here. So similarly, you can output a series of points with the same depth of R and call this the evaluation surface. This is what we mean the first step, to use the data acquired at the cable to predict the deghosted data at a shallower depth. Then we move to the second step. The second step, we like to predict the deghosted data on the cable. This is actually a Green theorem-based wave prediction theory here. So Dr. Wagner has given the tutorial. I'd like to quickly remind you that idea now, and then employ that idea to finish the step 2. So imagine you have a finite volume, and you have with the top boundary to be A and the lower boundary to be B. And your field P and the normal derivative of P are acquired at both A and B. So the medium is known, and that is chosen to be the reference medium. then you apply the Green's theorem-based integration over A and B. You can predict the wave field at any point inside the volume, for example, at R. So now this is what Green's theorem wave prediction communicates, and the theory was first provided by Wagner et al. In 2011. Now, if you imagine the medium inside is homogeneous and you have a wave moving up, then with the anti-causal Green's function to predict the wave field at any point inside the volume, what you need to measure is the field at the top surface, because the lower surface will not contribute. As this formula shows, by choosing G0 minus and grad G0 minus, the integration can be carried out along the top boundary A only. So next, we move to the experiment. It's exactly the same thing here. You have the predicted outgoing one-way wave from the first step as at this evaluation surface, and the objective is you like to deghost the data on the cable or predict the outgoing one-way wave at this cable. So what you need to do is just put a finite volume in the water and use the top boundary to be the evaluation surface. Then you do the surface integral in terms of anti-causal Green's function along the evaluation surface. You can obtain what will be inside. You can obtain what will be inside the volume, including for the point on the measurement surface. This is actually the theory of Stolt migration to predict the wave field from top to depths. And this is also the basis of Stolt extended Claerbout III one-way wave prediction. So with this method, you can output the deghosting result at the actual receiver depths, at actual receiver locations on the cable. And so now you can see we finished the second step to deghost the actual data on the actual cable. You may have one concern: how to compute the normal derivative of the P up along the evaluation surface. Among different options, one possibility is you can make the Green's function G0 to vanish along the evaluation surface to get rid of the requirement of the normal derivative. And there are other options. I refer you to my report. So now we have achieved deghosting the data on the cable. Next, I'd like to use a very simple example to examine this simple idea. And the model is you have a water layer and only one layered sediment. So the method is designed to deal with the cable to be non-horizontal. For sure, it can be depth constant. In this example, we like to examine the idea to the depth constant cable. Later, my colleague will show you the result with a non-horizontal cable. So just for one numerical test, we put the cable at 300 meters below, and first step, we predict the deghosted data at a depth 20 meters above the actual cable. And then the second step, we predict the deghosted data right on the cable. And with this model, we have the total wave field here along the acquisition cable. You can see this is the primary, which is moving up. You have the direct wave and the receiver side ghost, which is moving down. And for all these three events, there are source side ghosts. We are now looking at them at this talk. So now you input this data to the deghosting algorithm. In the first step, you can obtain this deghosted result that is at a shallower depth. If we compare the input and the output, you can see these downgoing waves disappear in the output result. So if we compare the primary of the input and output, you can see this primary actually is delayed in the output result. The reason is that the evaluation surface is actually shallower than the actual measurement surface. So the outgoing wave will continue their propagation with a longer traveling time. And we use this as the input to the second step. You can predict this deghosted data at the actual cable. You can see this is input, this is output. It moves advanced. And we can also compare the final result with the original input data along the cable. You can see this is the original data. This is the final result. The primary match very well. It means the method has successfully deghosted the actual data itself. Okay, so we can show you one single trace plot at offset 0 meters, and the blue line here shows you the total wave, and you have down wave. This is up wave. So the green line here shows you deghosted result at a shallower depth. You can see the down wave has been removed, and the up wave here, which is primary, is delayed. The green line is delayed than the blue line. So next I show you the result, final result from the second step. You can see the red line, which is shown as the red line. You can see the red line is overlapping with the blue line. Means we have finally deghosted the actual data. Okay, so next I like to use these two simple schematic diagram to draw the conclusion here. In this talk, we show you a new method with 2 steps to deghost the actual data on the cable, and without assuming the cable to be horizontal. Actually, it can be with a random shape. And the first step, we actually take the current deghosting method to predict the deghosted data at a depth above the cable. Then the second step is we using the one-way wave prediction to predict the deghosted data right on the cable. Okay, thank you.